Dear students, in the last class, we have studied about the non-aqueous solvents. In the non-aqueous solvents, we have studied their classification of non-aqueous solvents and also the liquid ammonia as a solvent. So the reactions in liquid ammonia also we have studied, like the acid-base reactions, precipitation reactions or metathetical reactions, solvolysis, solvation, and so on. Today we take another property in liquid ammonia, that is metal ammonia solutions and their reactions. Metals having low ionization energies, low energies of sublimation, and high energies of solvation, and even alkali metals, alkaline earth metals, aluminium, europium, and ytterbium, they readily dissolve in liquid ammonia and give metal ammonia solutions. These are blue in color in a dilute and bronze color in concentrated solutions. This is the very important property of metal ammonia solutions. The blue solutions are excellent electrolytes. By simply evaporating the alkali metal ammonia solutions, alkali metal can be recovered. Alkaline earth metal ammonia solutions on evaporation gives hexamonate complex. See, if you take alkali metals, alkali metal ammonia solutions on evaporation gives directly the alkali metals, but alkaline earth metal ammonia solutions on evaporation gives hexamonate complexes. All metal ammonia solutions upon long standing or in presence of a suitable catalyst undergo decomposition to give hydrogen gas and the metal amides. This is another property. The next property, the blue metal ammonia solutions are paramagnetic in nature, indicating the presence of unpaired electrons. The blue metal ammonia solutions act as a strong reducing agents. Many organic compounds undergo reduction in metal ammonia solutions. These are some of the other properties of the metals in liquid ammonia. Coming to the another non-aqueous solvent, that is liquid sulfur dioxide. So the reactions what you carry out in water, the reactions what you carry out in liquid ammonia, and similarly the reactions what you carry out in liquid sulfur dioxide as a solvent are different. Now let us study about the liquid sulfur dioxide as a solvent. Liquid sulfur dioxide is a water-like solvent used to carry out many chemical reactions. Its boiling point is minus 10 degrees centigrade and freezing point is minus 75.5 degrees centigrade. The auto-ionization or self-ionization of sulfur dioxide is as follows. So SO2 plus SO2 gives rise to SO2 plus, known as thionyl ion, and SO3 2 minus is known as sulfite ion. Here thionyl ion is analogous to hydronium ion or ammonium ion in water and liquid ammonia respectively. And sulfite ion is analogous to hydroxide ion and amide ion in water and liquid ammonia respectively. The dipole moment of sulfur dioxide is 1.61 D and its dielectric constant is 17.27 at minus 16.5 degrees centigrade. So the smaller dielectric constant shows that this is a good non-polar solvent. It can dissolve many salts. Now coming to the properties of sulfur dioxide. First one, solubility of inorganic materials in liquid sulfur dioxide. Alkali metal halides, sulfides, acetanates, acetates, sulfates, thiocyanates, and cyanides are soluble in liquid sulfur dioxide. The other metal sulfates, sulfides, oxides, and hydroxides are insoluble in liquid sulfur dioxide. The substances like iodine bromide, phosphorus tribromide, carbon tetrachloride, silicon tetrachloride, germanium tetrachloride, and tin tetrachloride are quite soluble in liquid sulfur dioxide. So here I have said about the solubility of inorganic materials in liquid sulfur dioxide. Now coming to the second, solubility of organic materials in liquid sulfur dioxide. The liquid sulfur dioxide has less dielectric constant compared to water. Hence, large number of covalent compounds readily dissolve as compared to ionic compounds. Aromatic hydrocarbons and alkenes are more soluble than the alkanes. Organic reactions like sulfonation, bromination, Friedel-Crafts reaction are carried out in liquid sulfur dioxide medium. Coming to the third property, that is conductivity of salt solutions in liquid sulfur dioxide. The solutions of alkali metals, ammonium and tetraalkyl ammonium chloride, bromide, iodide and thiocyanates are moderately good conductors. Many covalent compounds such as bromine, iodine, potassium pentabromide, antimony pentachloride, iodine bromide, iodine chloride, etc. behave as electrolytes in liquid sulfur dioxide. Students, you have to remember these reactions and which are the compounds they act as electrolytes. Coming to the important one, that is acid-base reactions. Just like water, liquid sulfur dioxide undergoes autoionization. That is, the two sulfur dioxide molecules, so they turn into the thionyl ion and sulfite ion. Thionyl compounds like thionyl chloride, thionyl bromide, that is SOCl2, SOBr2 act as an acid, and metal sulfides like sodium sulfite, potassium sulfite, cesium sulfite behaves like a base in liquid sulfur dioxide. It is just like the thionyl chloride is just like an HCl in water. HBr, thionyl bromide is like HBr in water. The sodium sulfite is just like NaOH in water, and so on. Thionyl chloride, SoCl2, which is an acid, combines with sodium sulfite, which is a base, in liquid sulfur dioxide. It gives sodium chloride as a salt and sulfur dioxide as a solvent. Similarly, thionyl thiocyanate, SCN is thiocyanate. Thionyl thiocyanate reacts with potassium sulfide in liquid sulfur dioxide, gives potassium thiocyanate as a salt and sulfur dioxide as a solvent. Coming to the another property known as solvolytic reactions. The solvolytic reactions in liquid sulfur dioxide are given below. The solvolytic reactions means they react. The solvent reacts with the other salts. Now, PCl5, when PCl5 is treated with sulfur dioxide, the liquid sulfur dioxide, we get POCl3, that is phosphorus oxychloride, and thionyl chloride is formed. That is, in general, if I say when a salt is treated with a solvent, we get the another salt and the acid is produced. The SOCl2 is nothing but it is an acid in liquid sulfur dioxide. Similarly, phosphorus pentabromide reacts with sulfur dioxide to form phosphorus oxybromide, and an acid, that is thionyl bromide, is formed. Similarly, uranium tetrachloride gives uranyl chloride. UO2Cl2 is known as uranyl chloride, and the acid, that is thionyl chloride, is formed. Next, sixth one, precipitation or metathetical reactions. Now, when potassium iodide is treated with thionyl chloride in liquid sulfur dioxide medium, so we get potassium chloride as a precipitate and thionyl iodide is formed. Similarly, the silver acetate, when it is treated with thionyl chloride is nothing but it is an acid in liquid sulfur dioxide, we get silver chloride as a precipitate and then thionyl acetate is formed. When ammonium acetate is treated with thionyl chloride in liquid sulfur dioxide, we get ammonium chloride precipitate and then thionyl acetate is formed. The next, that is complex formation reactions. A large number of complex formation reactions have been reported in liquid sulfur dioxide. For example, when potassium iodide is treated with iodine in liquid sulfur dioxide, we get potassium iodate. KiO3 is known as potassium iodate, which is a complex ion or the complex compound. Rubidium iodide, when it is treated with iodine, we get rubidium iodate. Similarly, mercuric iodide, when it is treated with potassium iodide in liquid sulfur dioxide medium, we get the potassium tetraiode. The tetraiodomercurate 2 complex is formed. Now coming to the another reaction known as oxidation reduction reactions. So the liquid sulfur dioxide is a good solvent wherein the redox reactions can be achieved. For example, when ferric chloride is treated with potassium iodide in liquid sulfur dioxide, ferric chloride undergoes reduction to form ferrous chloride, and then the potassium iodide undergoes oxidation to form iodine. This is because ferric chloride, here oxidation state is +3, it undergoes reduction so that oxidation state gets reduced to +2. Whereas potassium iodide, the oxidation state of iodine is -1 and it turns into the 0. So the oxidation number is increased. So we say potassium iodide gets oxidized to iodine. Similarly, antimony pentachloride reacts with potassium iodide in liquid sulfur dioxide medium to form the potassium hexachloro antimonate 3 complex ion, and also antimony trichloride and iodine is formed. Once again here the antimony having a oxidation state +5, it turns into +3, the number is reduced, hence it undergoes reduction. Similarly, the oxidation state of iodine in Ki is -1, it is increased to 0. In the product, it is formed iodine, hence oxidation state is increased, it is called oxidation. Here SbCl5 oxidizes Ki to iodine. So these are all some of the reactions in liquid ammonia. Students, here also in this slide I have given about the non-aqueous solvents. An inorganic non-aqueous solvent is a solvent other than water that is not an organic compound. Examples are liquid ammonia, liquid sulfur dioxide, sulfuryl chloride, phosphoryl chloride, antimony trichloride, bromine pentachloride, bromine pentafluoride also, hydrogen fluoride, other inorganic acids. These solvents are used in chemical research and industry for reactions. I have given here the liquid sulfur dioxide, it's the physical, the constants. Here I have shown the reactions in liquid sulfur dioxide, the acid-base reactions, and also the solvolytic reactions. Students, go through these reactions. Here we have precipitation reactions or metathetical reactions. So antimony trichloride reacts with lithium hydride to form antimony triiodide, which is a precipitate. Similarly, you also have solvation reactions. So the solvation reactions are also given in this. Students, go through these aspects and try to learn about these things by repeated